Sorry about this being in two parts. Unfortunately, the video cut off in the middle on me. So we need to justify how we know on example, I'm on the wrong example. This is example 2. We're on example 5, but they use the same equation. We need to justify how we know these are points of inflection. So you would tell me they're points of inflection because the second derivative equals 0 at these points, and the second derivative switches signs, so f switches concavity. So you can't just figure out where the second derivative equals 0, you must also figure out where the original switches concavity, so the second derivative switches signs. So let's look at example 3. Determine the points of inflection for f of x equals x to the 4th and discuss concavity. So to discuss concavity and points of inflection, you need the second derivative. So first you need to get the first derivative, and then you need to get the second derivative. So the first derivative is 4x cubed, second derivative is 12x squared. We need to find where it equals 0, and it equals 0 only at 0. So that could be a point of inflection, but now we need to do the sign test. And when we do the sign test, what do we notice about x squared? It's a double root. Let's see what happens. If we plug -1 into the second derivative, -1 squared becomes positive. If we plug +1 in, +1 squared becomes positive. Does the concavity, if this is my second derivative sign test, does the concavity on the original switch? No, it does not. So there is no point of inflection because the concavity does not switch. If you go back to the graph of x to the 4th from, I guess, algebra 2, maybe pre-calculus when you learn it, it looks like this, sort of like a flattened out parabola at the bottom. Notice it's concave up the entire time. There's no change in concavity, so there's no point of inflection. If we look at the graph on page 3, or the example on page 301 in your book, I'm going to do the work right here. You might have to do it on a sheet of paper. So they tell me f prime is greater than 0 from -infinity to 1, and f prime is less than 0 from 1 to positive infinity. So what does this tell me about the original? F prime tells me about the slope. So this tells me the original is increasing from here to here because that's a positive slope. And if the slopes are negative, then the original is decreasing from 1 to positive infinity. If they also tell me the second derivative is positive from -infinity to -2, and again from 2 to positive infinity. So this tells me that the original will be concave up on these two intervals. It also tells me the second derivative is negative from -2 to 2, which means it will be concave down. And then the last thing it tells me about is the limit as x approaches -infinity and the limit as x approaches positive infinity. Who remembers what we're finding when we find the limit as x goes to negative and x goes to positive infinity? Do you remember? That was from trimester 1. We are finding horizontal asymptotes. So the limit as x approaches -infinity, they tell me, is -2. The limit as x approaches positive infinity is 0. So I know that as x goes to -infinity, the y value is going to approach -2. As x goes to positive infinity, the y value is going to approach 0. So I have some horizontal asymptotes. So let's see. We know that this function is going to increase until 1. It's going to be concave up from -infinity to -2. So it should be increasing concave up until -2. It continues to increase until positive 1, but it switches to being concave down. Then at positive 1, it decreases the rest of the time. it's going to be concave down until positive 2. So it's decreasing, and then it switches to concave up, continuing to decrease. Notice each end approaches the horizontal asymptote. So that is a sketch based on the info they gave us. So let's move on to the second derivative test. So the second derivative test is a nice little test, and then I'm going to actually add 2 examples that you should be able to squeeze in at the bottom of your notes that are like how they're going to use the second derivative test on the AP exam. But the second derivative test says, if we know the first derivative at C is 0, let's just talk about what that means. What does that mean if we know the first derivative at C equals 0? It means the slope on the original at C is 0. What does that mean? What's happening on the graph of the original if the slope is 0? Where on that curve do I have slopes of 0? At hills and at valleys. So they're telling me the slope at C is 0. So we either have a hill or we have a valley. We don't know which, but it's one of them. Then they tell me the second derivative at C is greater than 0. If the second derivative is positive, what does that mean about the original? F is concave up. Which of these is concave up? A hill or a valley? So we know it's a valley, therefore it is a relative min. Walk through this. If the first derivative at C is 0, immediately that's telling me I've got a hill or a valley. And the second derivative is negative. Immediately that means the original is concave down. Which one of these is concave down? The one with the hill. If it's a hill, then I have a relative maximum. So this is what an example would look like. I'm going to put the examples up top so you can see it better, but you probably can squeeze them in at the bottom. I strongly recommend you write these down. You never know when you'll see something like this again, okay? So let's suppose you're given f prime of 2 equals 0. F double prime of 2 equals 8. And the question is f of 2 a relative max or relative min? Notice, I have no equation to work with. So I've got to figure out if f of 2 is a relative max or a relative min, and I have no function to work with. And I'm going to do it based on this information. The first piece tells me the slope at 2 is 0. What does that tell me about the original? The slope is 0. If the slope is 0, the original must have a hill or a valley. It's got to be one of them. Then it tells me the second derivative at 2 is 8. If the second derivative at 2 is 8, that means the second derivative is greater than 0. Does that mean the original will be concave up or concave down at 2? It will be concave up because it's positive. So is it going to be a hill or a valley? It's going to be a valley. If it's going to be a valley, is that going to be a relative min or a relative max? It's going to be a relative min. Good. Example B. We've seen this on the AP before in a multiple choice. Given f double prime equals 2x minus 3, is f of 0 a relative max or relative min if we know f prime of 0 is 0? We don't have the original curve. All we have is the second derivative function. And at this point, you don't know how to get from the second derivative equation back to the first. You will learn that in another week or so. But then what I'll start doing is giving you second derivative equations that you don't have the ability to convert back to the original, because that's what they'll do in the AP. So what do we know? What do we know about this original curve? We know the slope at 0 is 0. So if the slope at 0 is 0, what do we know is happening at 0? We know it's got to be a hill or it's got to be a valley. Which one is it? That depends on the concavity. Second derivative tells me about the concavity. We want to know the concavity where? at 0. So we're going to plug 0 into the second derivative, and we get -3. So the second derivative is less than 0. So what's that mean? It means it's going to be concave down. So it's a what? F of 0 is a relative max because it's at the top of a hill. Good. Good. So let's move on to the last page of examples. Okay, so for this one, typically I would have y'all in here to help me remember all the information, and your notes would be right here, but we are virtual, so let's see what I can remember. We've already done all of the work we need for this. We were given this yesterday. It was example C. It was a C that I added, where we found the first derivative sign test. So I'm just going to recreate, it's in your notes from yesterday. We had zeros at 0 and 3, and it was a double root, so it was negative, negative, positive. So we had a relative min at 3, -27. Then today we did the second derivative sign test, which was at 0 and 2. I don't remember the sign test, but we can do it real quick. The second derivative is 12x squared minus 24x. So we pull out this and we get x minus 2. So when we do a sign test, we get positive sign. So the middle was negative. So we had points of inflection at 0, 0, and at 2, -16. Okay, we want to sketch a graph using this information. So let's see. The first thing we probably want to put on here is any max and min. So we have a minimum at -27. I'm not going to count out 27 tick marks. I'm just going to say -27 is way down here. Let me put my minimum down there. Okay. We also have a point of inflection at 0, 0. And we have a point of inflection at 2, -16. Right about here. So then we're going to sketch a graph based on what we know. Well, we know in the beginning the slope is negative, and it stays negative until 3. So this thing should decrease until we get to 3. It should be concave up until we get to 0. So it should decrease and be concave up until 0. At 0, it still decreases, but it's concave down. So now we're going to curve and be concave down. And then at 2, it's going to switch to concave up, but we're still decreasing. So we're going to see, oops, a concavity switch, so it's curving up. And then it's continuing to curve up, but now it increases. What does that sort of look like? Looks like a wonky W, doesn't it? We got a little bit of a W shape, but it's like it got all smushed and twisted. It's an x to the 4th graph. So it should look a little like a W shape. So let's move on to the last 2 examples. Use the graph of f prime to answer these questions. Well, for many of you, as we work through these, you will discover that you can answer all these questions just by looking at that f prime graph. But a lot of people, looking at the graph and answering questions, it starts to get jumbled in your brain, the information, because it's a little more abstract. So if we can put this in terms of something concrete, like a sign test, it gives us a tangible way to hold on to the information and keep everything organized. So I'm looking at f prime, and you want to get in the habit of circling or highlighting what you're looking at. Because on the AP exam, they might give you a graph of f, they might give you a graph of f prime, they might give you a graph of f double prime. It's very important you know which one you're looking at. So I'm looking at the graph of f prime, so I'm going to make myself an f prime sign test. I am looking at f prime. F prime equals 0 right here. That means the slope of the original is 0. F prime equals 0 right here and right here. So I'm going to put my critical numbers, my zeros, on my sign test. Now, what are the values of the f prime curve right here? What are the values? When x is -3, what is that y value? Positive. When x is -2.5, what is that y value? Positive. So f prime is positive. What are are the y values down here for f prime? They are negative. What are the f prime values up here? Positive. And then again, when x is 3, f prime is negative. When x is 5, x prime is negative. So we have a sign test. So we now can answer anything about the slope of the original. The original is going to increase, decrease, increase, decrease. So where does the original have a relative maximum? Is the relative maximum at this hill? No, this hill has nothing to do with f. This is f prime's hill. We want to know where f has a hill. It has a hill at -2 and 2. So at x equals -2 and 2. How do we know? Now we justify. How do we know there's a relative max at -2 and again at +2? Because f prime switches from positive to negative values. Therefore, f changes from increasing to decreasing. They'd ask for minimum, you have a minimum at x equals 0. Part B, where does f have any points of inflection? Well, what talks about points of inflection? Not f prime, f double prime. We don't have an f double prime graph, but we can make an f double prime sign test from the f prime graph. Because f double prime, second derivative, measures concavity of the original, but what does it measure about the first derivative? The derivative of the derivative measures the slope of this graph. The second derivative measures the slope of this graph. So what is the slope right here? The slope is negative, so the second derivative is negative until I get to here, where the slope is 0. So the second derivative will be negative until -1. Then what are these slopes? What's f prime doing here? F prime is increasing. So the second derivative is positive because f prime is increasing until we get to another slope of 0 at 1. And then it decreases again. So now the second derivative measures the slope of f prime, and it tells me about the concavity of the original. So the original is concave down, concave up, concave down. So where does the original have any points of inflection? It has points of inflection at x equals -1 and 1. If I asked you to justify it, how do you know? You would tell me because the second derivative equals 0 and switches signs. How do we know? We know that because f prime goes from decreasing to increasing and increasing to decreasing at those points. So you've got to relate it to the graph they give you. So yes, you can say because the second derivative changes signs because the second derivative measures the slope of the first derivative, which goes from increasing to decreasing to increasing. Where is the original going to be concave up? It's concave up from -1 to 1. How do we know? Because the second derivative is positive. And we know this because the first derivative is increasing. So we got to put it in terms of the graph that they gave us. We got to explain where we got our f double prime info from. We know the second derivative is positive because the first derivative is increasing. So last example is a position function. Given the position function, when does a particle speed up? Well, to what tells me about speed, first of all? Velocity. So we need our velocity. So let's start there. So our velocity function is 3t squared minus 10t plus 4. This is the same velocity function we had yesterday. So if you go back to those notes, this was our velocity sign test. We started at time 0. We went to 0.465 and it was positive. Then it was negative until 2.86 something, I think it was 9. And then it was positive again. So we know this thing is moving forward, moving backward, moving forward. We want to know when it speeds up. How do we tell if something speeds up or slows down? Who remembers from before Thanksgiving? An object speeds up when velocity and acceleration have the same sign. And then it slows down if the signs are opposite. So we know the velocity signs. Whose signs do we need to know? Acceleration. So we need the acceleration equation, which is the derivative of the velocity. So 16 minus 10, got to find where it equals 0. So 10/6, which is 5/3. 5/3 is 1 2/3, so 1.6 if we want to use decimals. Okay, time still starts at 0. We have to do a sign test. Plug in 1 to my second derivative. This is the acceleration sign test. Plug in 1, we get 6 minus 10 is negative, then positive. So this thing is going to speed up when velocity and acceleration have the same sign. Velocity starts out positive, acceleration starts out negative. So what will the object be doing? Slowing down. At 0.465, velocity switches to negative. Acceleration is still negative, so what will it do? Speed up. So it's going to speed up beginning at 0.465 until velocity stays negative, but acceleration changes to positive. So it's going to speed up until 1.667, where they're opposite again. Are they opposite forever? No, they're going to both be positive again, beginning at 2.869 until forever. So this object is going to speed up during these two time intervals when velocity and acceleration have the same sign. They ask for a justification. All you would have to say is you know this because velocity and acceleration have the same sign.